Hi everyone, my name is Ryan Marcus. I'm a postdoc at MIT CSAIL, where I work with Tim Kraska. I'm also a researcher at Intel Labs. Today I'm here to talk to you about Bao, our new system for learned query optimization. Query optimizers work by taking in a user-submitted query and running a whole bunch of heuristics and cardinality estimates and advanced dynamic programming search algorithms in order to spit out a query execution plan. That query execution plan is then handed off to the execution engine, which is responsible for executing that plan against the underlying data and delivering the result back to the user. But in addition to observing the query result, the execution engine also observes the latency of the query. For a very long time, the database community has known that there should be some way to use that observed latency from the query execution engine to continuously improve the query optimizer in a sort of feedback loop. However, the problem has been elusive, and a lot of the solutions the database community has come up with have met some practical barriers. One of those solutions was our own work that we called NEO. NEO replaced the entire query optimizer within a database system with a deep reinforcement learning powered system. NEO had some very promising results, but like a lot of other proposals at the time, it also came with three really big issues. The first really big issue that NEO had was sample inefficiency. By sample inefficiency, we basically mean NEO took a really, really long time to train. In ideal conditions, NEO could take up to 32 hours to become competitive with a simple optimizer like the one found in Postgres. This might be fine depending on your use case. However, NEO and other solutions like it also suffered from a large degree from brittleness. Changes to your underlying data, the schema of your database, or even your query workload could result in a model that you spent a very long time training suddenly being invalidated. Specifically in the case of NEO, if your schema changed, you'd have to totally throw out your model and train your data again. Turns out practitioners like to modify their data more than once every 32 hours, so this approach ran into quite the problem. In addition, the third biggest problem that NEO and approaches like it had is what we call tail catastrophe. While all of these systems are really, really good at decreasing the average query latency of a given workload, they're not so great at decreasing the tail latency, like the 99th percentile latency of your system. In fact, in a lot of cases, they can make it significantly worse, up to 2 or 3 times worse, is what we observed with NEO. This is obviously a huge problem for practitioners who are often concerned with tail latency because, that tells you kind of the worst case scenario for how your system is going to interact with like a customer or something. So in order to solve these problems, we're now introducing Bao, which is the bandit optimizer. Bao works by steering instead of replacing a traditional query optimizer, and using the techniques that we've discovered with Bao, we can outperform the Postgres optimizer with just 1 hour of training time, while simultaneously reducing 99th% tail latency, and we can do it all while adapting in real time to changes in workload, schema, and data. The easiest way to gain an intuition for how Bao works is to walk through how a DBA might approach a slow-running query. So imagine that you're a DBA, you submit a query to your database, and you observe, hey, this query took a minute to execute. And you might think for this particular query, based on your knowledge of the database, that that's just a little bit too slow. Something doesn't quite add up there. So you'll run that same query through the explain functionality of the query optimizer, and you'll see what kind of query plan is being generated. You might notice that in this case, Postgres chose to use a loop join plan, but you know that query should have relatively low selectivity, so it doesn't really make sense to use a loop join plan with lots of indexes. So the next thing that you can do is you can try disabling loop join inside of your Postgres session and re-executing the query. In this case, you might discover a huge improvement. The query went from 60 seconds of execution time down by a factor of 3 to just over 20 seconds. That's really good. You know that the optimizer now made a mistake, and you would like to preserve this hint. So one option would be to apply that hint globally and just say, okay, maybe there's something wrong with the Postgres optimizer that it always chooses loop joins when it shouldn't. But this will obviously lead to other problems. Different queries that make good uses of indexes and good uses of loop join plans might regress significantly. So, for example, a different query might go from taking just under half a second to taking almost 20 seconds again, a huge increase in what used to be a very, very fast running query. So, obviously, you have to revert that change because you caused way too many query regressions, but now what can you do? Well, one of your options is to go through your entire code base, find all of the queries like the first query, and add this hint manually to that query. Your second option is to set the no loop join hint as a default, go through your entire code base, find every single regression, and add a hint that turns loop join back on for those queries. Or you could do what most DBAs do in this situation, give up. Bao is designed to produce a fourth option that we hope is a little bit better. Bao automatically determines the right hint set to use for each incoming query, and the way that it does this is by considering different query optimization hints as armed in a contextual multi-armed bandit problem. So, for example, when a query arrives to the system, we'll use the traditional query optimizer, but instead of generating a single plan, we'll generate a whole family of plans. For example, we might generate one plan that uses a loop join, another plan that uses a hash join, and a third plan that uses a merge join. Once we've generated all of these candidate queries without actually executing any of them, we'll run them through a performance prediction model. And that performance prediction model will say, hey, I think that loop join plan is going to take 20 seconds. I think that merge join plan is going to take 18 seconds, etc. Then, once we have all of these predictions from our performance model, we'll simply pick the one with the lowest expected execution time, and we'll send it off to our execution engine. Our execution engine will then execute that particular query, and then we'll be able to see how well we did. In this case, we guessed that the query would take 18 seconds to run, but in reality, it took 38 seconds to run. It's obviously a mistake, so we'll add that training pair into our training data and hope that we do better next time. There are two major components to Bao. The first is its predictive model, and the second is its training regime, and I'm going to talk about them each in that order. So Bao needs a really good predictive model in order to go from these query plan trees to the predicted latency in an accurate way. The problem here is that query plans have a tree-like structure, and most of the machine learning tools that we can get off the shelf expect a vectorized flat input. One solution to this, which is very common in the literature, is to flatten that tree into a vector and engineer some features along the way. This is not normally how machine learning is effective. If we look at the domains where machine learning has worked really, really well, like computer vision and natural language processing, we can see that the models that they choose map much more closely to the structure of the problem that they're undertaking. For example, in computer vision, convolutional neural networks represents a very fundamental operation that you might perform on a two-dimensional signal. In the field of natural language processing, attention mechanisms can very naturally represent the kind of long-term dependencies that we see in a lot of those NLP tasks. In the machine learning parlance, we call this kind of property an inductive bias. So we say that convolution has a good inductive bias towards computer vision tasks because convolution can naturally represent the types of features that we think are useful in those tasks. Similarly, attention mechanisms have a good inductive bias for natural language tasks because attention mechanisms can represent long-term dependencies in a way that's fairly succinct. The bottom line here is that machine learning models work best when the model structure matches the underlying structure of the task. Therefore, for Bao, where our fundamental structure is a query plan tree, we choose to use tree convolutional neural networks as our model of choice. We use tree convolutional neural networks as well in the NEO work, the prior work to this one. And if you'd like to check out details about why tree convolution represents a really good inductive bias for query plan trees, I recommend you take a look at the NEO paper. The link is there. If you're more interested in the implementation and seeing some results directly, we also have an open source implementation of tree convolution, which is available at the second link below. But overall, because tree convolution makes itself a pretty good inductive bias towards these query plan trees, they work as a good predictive model for Bao. The next thing that I want to talk about is how this predictive model is trained. Where does the data come from? If you're using Bao, you have two options in order to train it. One of them would be to gather a gigantic query log that has a whole bunch of plan pairs of this query plan took this long to execute. You can gather a whole bunch of those from as many sources as you want, and then you can try to, in one shot, train a really general purpose model that you then deploy out to your various databases. This might be considered the easier approach in terms of you have a lot of control over the process. You might already have access to query logs, etc., but it doesn't really adapt very well. If you don't have any examples of a particular type of query inside of your training set, that model is unlikely to make good predictions about them in the future. The second option, and what we do for the majority of the Bao paper, is to periodically retrain the model online using a reinforcement learning technique called Thompson Sampling. So before getting into the details about how Thompson sampling works, I want to first highlight why we need Thompson sampling in the first place. If we're retraining the model actively during query execution, during query processing, not during query execution, we need to balance exploration of new policies with the exploitation of what we know works. For example, if you only prioritize using exploitation, in this particular scenario, you might always simply pick the lowest predicted query latency. So for example, you might choose to only execute the loop plan. You'll pass that loop plan onto the execution engine. The execution engine will execute the plan, and it might come back and say, yep, the latency was 9, just as you predicted. Then you'd store that information in the model, you would retrain it, and the next time that query came along, it would again produce the exact same predictions for each one of the plans for that query, and you would again pick the loop plan, which would again execute in 9 seconds. The problem is, while the loop plan prediction is really, really good, the hash plan and the merge plan predictions might be totally wrong. It might be the case that the hash plan will execute in just 3 seconds, significantly faster than the loop plan. But if you use a strategy of pure exploitation, where you only ever pick the lowest value that the model predicts, you'll never discover that. You'll never have the training data that tells you that the hash plan would actually be faster. So, on the opposite end of the extreme, we could maximize for exploration instead. When maximizing for exploration, what we would do is simply choose randomly. Each time the query arrived, we would just randomly pick one of the 3 plans, each with the probability of 1/3. So maybe the first time we run a loop plan, the second time we run a hash plan, third time we run the merge plan, or something like that. If we do this repeatedly over and over and over again, our model will see a very high diversity of data, and it will become more and more accurate, but we won't actually be able to take advantage of what the model learned in any meaningful way, because we're just continuing to pick randomly. So how do we balance these two things? How do we do enough exploration so that our model can become accurate, while also still doing enough exploitation so that the system actually improves and gets faster? Well, one way that this is very commonly done in the literature is by using what's known as a fuzz factor. The basic idea is you take the outputs of your predictive model and you softmax them and turn them into a probability distribution and then pick from that probability distribution, or you add a small constant, possibly negative, possibly positive factor to each one of your predictions, and then you pick from there with some degree of randomness in it. This approach is not amazing because it doesn't respect the confidence or the certainty of the model. So for example, with the approach where you add a constant possibly positive or possibly negative fuzz factor to each value, if the loop plan prediction is really, really, really confident, but the hash plan prediction is really, really, really not confident, then adding the same constant fuzz factor to both doesn't induce the probability distribution that you hope it would. The fuzz factor doesn't respect the certainty of the model. So one solution to this problem proposed by the literature is Thompson sampling. Now, when we do Thompson sampling, what we do in this case is we always pick the lowest prediction from the model. We always choose the query plan that the model says is going to perform the fastest. However, we move the fuzz factor from which query plan we pick into the model itself in a way that respects certainty, so that the model itself will output results such that if we always pick the lowest one, we will balance exploration and exploitation. So the easiest way to see how this works is to think a little bit differently about how we train machine learning models. So first thing I want to note is that Thompson sampling is not a new contribution from us. It's a really old, well-studied algorithm for balancing exploration and exploitation. In the Bao paper, we cite a really awesome survey paper that will go through all of the mathematics that I'm about to go through with way more in-depth proof than intuition. I'm just trying to give you a high-level overview today. So if we think about our usual machine learning training, we know that if we apply our usual machine learning training and then we always pick the lowest predicted latency, what we'll end up is maximizing exploitation. So another way of thinking of doing that usual ML training, which results in maximizing exploitation, is by choosing the model weights from a distribution. So we have some distribution, the probability of our model weights given our data, that says, hey, these model weights, they're really, really likely for your particular underlying data. And these model weights, they're really, really unlikely given the data that you gave. Well, when you do traditional machine learning, what you're doing is you're taking the expectation, you're taking the modal value of that particular distribution. In other words, you choose the model weights that are most likely given your data. In addition to maximizing exploitation, we can also train a model that will maximize exploration. To do this, we pick the model weights at random according to the prior distribution of the model weights. This results in a model that outputs a totally random value for every single query plan that we put into it. If we then pick the query plan with the lowest predicted latency, we'll be choosing a random query plan. The beauty of Thompson sampling is that we can actually choose a model that balances between exploration and exploitation by slightly modifying how we generate our model weights. Instead of choosing the expectation of the distribution of model weights given the data, or just choosing randomly from the probability of the model weights, we can instead sample from the distribution of the model weights given the data. By sampling from the conditional distribution of the model weights given the data, what we'll end up with is model weights that respect the certainty of our underlying data. If we have a ton of data suggesting that a particular query plan, when ran with a loop plan, will have an execution time of 10 seconds, then our model weights that we sample are very, very likely to predict 10 seconds for that particular plan. If our data has almost no information about a particular query's performance with a hash plan, the model weights that we choose overall, statistically, will assign a random value to that. In this way, when we choose the lowest predicted latency query plan, we'll end up balancing exploration and exploitation in a way that respects our model certainty about the underlying data. The last thing that I want to say about Bao before we get into some experimental results is how easy it is to extend Bao. If you come up with a new cardinality estimator or a new feature or a new latency predictor that can describe a particular node of a query plan tree, that can be very easily added in as a new feature in Bao's tree convolutional neural network. And Bao will automatically incorporate that new information into its decision making. For example, say you create a new cardinality estimator, but you're not really sure if it's going to be better than your original cardinality estimator all the time. You can put that new cardinality estimator into Bao, and Bao will automatically determine maybe it's always better, and Bao will stick to using that cardinality estimator. Maybe it's never better, in which case Bao will automatically ignore it. Or, the most likely scenario, maybe there are some conditions in which your new estimator works really well, and some conditions in which your new estimator doesn't work very well. Bao, through its tree convolutional neural network, has a very, very high chance of discovering when those conditions are and automatically choosing when to use that new feature or when to ignore it. In addition to new cardinality estimators or latency models, you can also add entire new optimization strategies into the mix. For example, let's say you create a new type of join or a new type of index. You can simply add an arm into Bao that says use my new type of join or use my new type of index, and Bao will automatically figure out which queries it should be applied to or which queries it shouldn't. There's one caveat here, which is that adding a new option makes the number of arms in the bandit go up exponentially. This is totally manageable, and Bao can handle a pretty large number of arms, up into the hundreds, but eventually you won't be able to just add more and more things into it. It's probably still easier than dealing with integrating your new algorithm fully into a traditional query optimizer, though. Next, I want to go over a few of the most critical experiments that we performed in order to evaluate Bao. Plot on the right-hand side of the screen shows the various times it takes for a Postgres database without the Bao optimizer and a Postgres database augmented with the Bao optimizer to perform a couple of different workloads. These workloads all have varying degree of dynamism, ranging from dynamic queries that are executed throughout the workload to dynamic data and even schema changes. In each case, Bao is able to significantly decrease the time required to process the entire workload compared to Postgres. And again, this shows that Bao is capable of handling dynamic workloads, dynamic schemas, and dynamic data easily in an adaptive way. Of course, Bao does come with some overhead. In order to train the tree convolutional neural network most effectively, you have to attach a GPU to whichever instance you're using to operate your database to perform your model training, and that can add some extra cost. So in order to compensate for this, we also looked at the cost of executing each one of these workloads on a cloud platform, in this case, the Google Cloud Platform. And while the advantage that Bao shows in terms of cost is slightly less than its advantage in terms of time, they are approximately proportional because the Bao training procedure is relatively cheap. There are a lot more experiments in the paper, including analysis of training time, model accuracy, and tail latency performance. But I actually want to talk about an experiment that we did after submitting the paper that I think is really interesting. We started to expand Bao to work on distributed systems as well as just single node systems. So we looked at systems like Vertica, TP2, SQL Server, and Redshift, and we tested just our vanilla version of Bao with no modifications whatsoever except for new hint sets. On our same workloads in these distributed settings. Now, for each one of these databases, we ran them on their preferred cloud. So we ran SQL Server on Azure, we ran Redshift on Amazon, etc. And for each one, we created the cheapest possible 3-node cluster that we could in order to evaluate the performance of these queries. So don't compare between systems because they're all running on different hardware. Just look at how Bao adapts to that particular system. This suggests that different commercial systems have drastically different capabilities and query optimizers that are good at doing different things. This isn't a huge surprise, but what is a huge surprise, at least to us, was that Bao with no modifications was capable of working in these distributed environments on state-of-the-art distributed systems as well as on single-node systems. So with that, I highly encourage you to check out the paper. You can find it in the SIGMOD proceedings or at the link here. You can also find my personal website as well as my Twitter. And if you like this research and you think it could be interesting, I am looking for a job, so please do reach out. Thank you.